All right, this should be a fairly quick lesson, especially since we have access to a GDC for anything we want, and a lot of these things in this, once you understand some of the terminology, our GDC can do a lot of it. So just a new phrase, a stationary point. Very similar to a turning point. A stationary point is anywhere where your derivative at that is 0 at that point. So for example, I look at this function here, there are 4 stationary points. Now 3 of them are turning points. There's a turning point, there's a turning point, and there's a turning point. However, this point here does have a derivative of 0 at that point. It does have a horizontal tangent, but it's not a turning point. If you look at what's happening for this function at this point, it's going down, it flattens out for an instant, and then it just keeps going down. So it doesn't turn, it's always going down except for that one instant where it's just has a horizontal tangent. So we call this an inflection point. We've heard that before. A little better, it's called a horizontal inflection point. There's also a vertical inflection point, which actually will come into play at some point of a question today. Other than that, sometimes we can use our derivative, sometimes we can just look at the graph to figure out where these are. So let's look at this 5th degree polynomial that's been graphed already. And we want to identify and classify all the stationary points on this graph. So I can just tell by looking at it, whether it's from this or from a GDC. I can see there seems to be some sort of stationary point there, seems to be a stationary point there, and there's also somewhere around here, there seems to be a horizontal inflection point. Now those are the ones we can't directly tell from a GDC, because keep in mind, just finding a maximum or a minimum on our GDC we've learned before, and we should be fairly quick at that. But somewhere in here, there seems to be a horizontal tangent. And it's hard to tell if there really is. So in this case, our derivative comes into play. And so if I look at this, if I want to, my derivative, it's just a bunch of uses of the power rule. So we should be quite quick. Should get 20x to the power 4 minus 180x cubed plus 360x squared plus 80x minus 480. So this can be helpful to figure out where that inflection point is and to confirm there really is an inflection point. So I want to graph this. In fact, I'll show both graphs. And so here's the graph of the original function, which is a terrible graph right now because my y-axis needs to be compressed greatly. So we adjust our y min and max to get a sort of scale that I can now get a sense of things. And so there I can see, without needing a derivative, I can see that there are stationary points or a local max and a local min at these places here. So maybe I'll write that down right now. And so I don't need the derivative for that, although I will connect it to a derivative. So I know at negative 1, 1,501, there's a local max. And at 6 and negative 1,536, there's a local min. These are just local max and local mins because if I just look at the graph, even from what's been given on the page, I can see there is no maximum. There is no global maximum. It goes up forever. There is no global minimum. It goes down forever. All right, what about that inflection point? Well, for that, I need to look at the derivative. So I graph the derivative as well. You can see the derivative in red. Notice a few things. Where my derivative equals 0 at negative 1 and 6, that just confirms what we already saw, that there's a stationary point when x is negative 1 and x is 6. But I can now confirm there is indeed an inflection point right there when x is 2. So when x is 2, and on my function when x is 2, y is 768, that is an inflection point or horizontal inflection point. And it was really just for that the derivative was quite helpful. So I can tell at 2 and 768 is a horizontal inflection point. All right. So next, I have this function here. I've called it f of x. It's negative x squared times the natural logarithm of x squared. So we have a we have a quadratic function inside a logarithm being multiplied to another quadratic function. But we got this sort of fairly pleasant M-looking shape here. I want to find the coordinates of all the stationary points. Now, we got to be a little careful here because it is easy to look at here and go, there's a stationary point there, there, and there, just from looking at the graph. There is one mistake with what I've just mentioned. So let me first just graph this in Desmos as well. So let's turn these these off, and let's turn this on. All right, so let me adjust my scales, and that's actually pretty good, just like that. Okay, and so just from looking at this, I can see there is indeed stationary points at these coordinates of plus or minus 0.607 approximately, both at a y value of 0.368. All right, so let me write that down, but there's something we gotta be careful about that seeming local min over there. But I'll hold you in suspense. And so I got plus or minus 0.607 and 0.368. These are our stationary points. In fact, they are both global maximums. They're kind of a tie. And those are these points here. And that's accurate to 3 significant figures. Now for this one, if I want to look at the derivative, to be honest, as an SL student, we will never be expected to differentiate this. As an HL student, you will be expected later on. It gets fairly messy, but since this is an SL lesson, I'm not going to go into derivative of that because we don't really need to for this question. And even if you know how to differentiate it, it does get pretty messy. But just from my GDC, I can see those two maximums there. So this here, what's the issue with that point there? Well, Desmos is pretty fancy compared to a lot of GDCs. And I get a sense, if I put my point, if I kind of drag it here, you notice it's actually undefined right at 0, which means this function doesn't actually exist at 0, which means we can't say 0, 0 is a stationary point. This function doesn't exist here. So why is that? Well, the key is we don't need a GDC for that. If we look at our function, when x is 0, I have the natural logarithm of 0. And remember, you can't put a 0 into a logarithmic function. The natural logarithm of 0 is the same as log base e of 0, which means e to the power of what equals 0. That ain't gonna happen. And so that's not possible, which means the natural logarithm of 0 is not possible, which means I can't put 0 into this function, which means this function isn't defined there. So if I want to make my graph a little bit more accurate, I'm going to put a little hole there and draw a little point of discontinuity around it. And so at this point, by using Desmos, you could see that, but really we need to realize that I'm just going to make a point that 0, 0 is not a stationary point. And that's because f of x is not defined when x equals 0. So that's it for that first part. That's it. Determine the global maximum. Well, I've already said, actually, the global maximum were these 2 points here. The global minimum does not exist because this function just keeps going down and down forever. So this function has a tie. Its global maximum is approximately 0.368 at plus or minus about 0.6 on the x. There is no global minimum. Which means there's also no local minimum because, again, right here, you may be tempted to say, well, that's a local minimum, but again, that point doesn't exist, but yet you can get infinitely close to the left and the right from that point. So deceivingly abstract little question here, but I'll go back to that drawing. All right. Lastly, find the smallest and largest value of y equals the ln of 4 minus x plus 2 ln x, but just between 1 and 3. And again, this is something in which we can mostly just use our GDC. I won't actually need to differentiate here. So first, let me graph this function here. But keep in mind, let me turn this on. If I look at this function just here, this is the graph of ln of 4 minus x plus 2 ln x. However, this is the whole function. I only want from 1 to 3. And so let me adjust I'll leave it like this. So one option on your GDC is just to have the y min and y max, x min and x max set to 1 and 3. That said, you should see something that just looks like this. Which I'll leave the old graph in the background just as for reference. But all I really need is what I see here. And so if I look here, what is the maximum and minimum of this? And so actually, I will turn that off. So if I look here, I can definitely tell it does reach a peak before I reach this endpoint. And so fairly quickly in your GDC, you should be able to see that there is a maximum at this point of about 2.6 repeating on X and about 2.25 for the Y. So, and that is the highest point. Just barely, it's higher than anything around it. So let me write that down. So the largest value is when Y is approximately 2.25, and that's when X is approximately 2.67. All right, what's the smallest value? Well, if I look at the entire graph, if I look at everything, there is no smallest value. It just goes down forever. But we're not looking at everything, we're just looking at this. And so I just need to pay attention to my endpoints. And I can definitely see that's going to be the lowest point there. When X is 1, Y is about 1.09, about 1.10. Over here, when X is 3, I'm definitely less than my maximum. So that there is not an absolute, it's not a global maximum or minimum, I should say. But this point here is my absolute or my global minimum. Too many words. And so the maximum point is right there. The minimum point is right here. And so let me write that down. So the smallest value is about 1.10 to 3 significant figures, and that's when X is about, that's when X is not about, that's when X is exactly 1. It's one of our endpoints. And so keep in mind, in general, if we look at a graph, if we ever want to figure out where its maximum or minimum values are, we definitely want to pay attention to stationary points, but also, unless the graph goes on forever, we want to pay attention to its endpoints, in this case, 1 and 3. Whereas if the graph just kept going, there would still have the same largest value, but there would be no minimum value because it just keeps going down forever.